In this sequence, we will cover the impedance model. In the sequence, you will see your next big aha moment in this course. Okay, the readings for this section are 13.3 from the textbook. So far we've been looking at trying to figure out the response of circuits to various kinds of drives, and in particular in the most recent section we looked at sinusoidal steady state and looked at sinusoidal drives. So we said, let's take the usual approach, which is trying to climb the face of a mountain with differential equations and DEs and all of that stuff, which is really, really hard. So we said, hey, we found this path through the back here, which was another method, a sneaky path where we introduced a drive of the form e raised to st, and we found that we still had to do differential equations, but we avoided a whole bunch of complex trigonometry. In this sequence, you will see a spectacular new method, called the impedance method. And in this method, you will notice that you will even find the sneaky path to be hard. And in this path, you will completely do away with differential equations and get to the top very, very easily. Okay, so let's dive right in and take a look at what this amazing method is going to look like. Let's start with a review, as is our usual practice. The circuit we've been looking at in the sinusoidal steady state analysis of ours is this voltage source resistor capacitor circuit, where our goal has been to find the voltage across the capacitor. Okay, and we said, let us focus on sinusoidal drives. So my amplitude here, VI, is real. So I take a real value here. And so my input is VI cosine omega t. In sinusoidal steady state, we focus on sinusoids, as I said. And the reason we want to focus on sinusoids, they're a very important kind of waveform. For one thing, you can take repetitive waveforms such as speech signals or square waves and other waveforms and represent them as the sum of sines of various frequencies. So once you know how to work a sinusoid, then you can pretty much obtain the response to other repetitive signals by summing up the responses to each of the sines by superposition, as long, of course, you have a linear circuit. Okay. The second thing as part of a sinusoidal steady state was steady state. And we said that, in practical circuits, when we look at sinusoidal analysis, we really care about the behavior of the circuit after a long period of time. Okay, after all the transients have died away. Okay, so who cares what the initial conditions look like? Who cares about the initial response of the circuit? It's like when you switch on an amplifier, you may hear some distortion, but very quickly that goes away, and then you hear pristine sound following that. And so really, it's about finding the particular solution Vp, which is the response to my input, all right, after all the transients have died away. Okay, so we're looking at steady state solutions. In other words, we're looking at the particular solution to our circuits. In doing so, we said, let's take our usual approach. Okay, we started off with the differential equation approach, and we said what we'll do is we will build our usual circuit model. Okay, we will go ahead and in step one set up the differential equation, and then we discovered that we ran into a nightmare of trig. Okay, but if you went through that trig, you would end up with your answer. It would be some sinusoid at the output. Okay, so if you have a sinusoid at the input, you would find some sinusoid at the output as your response, but the sinusoid would have a different phase and it would potentially have a different amplitude. Okay, but it would still be a sinusoid at the output. Now we said that was way too hard. Okay, we wanted to find an easy approach to do it. So we said, let's try this trick. Okay, so we said, let's take a sneaky path. So by taking this sneaky path, what we discovered was that we could get rid of our trigonometry. And what we did was we introduced a sneaky input, Vi e raised to j omega t. And by and large, I want you to recall, we also use a shorthand notation, V raised to e raised to st, where s, okay, is a shorthand for, that's not clear. Let me just clean that up a little bit for you. Where s is a shorthand notation for j omega. So we sneak in our Vi e raised to j omega t, or Vi e raised to st drive. And then what that does is we found that for an exponential drive, the responses were also exponential, and that resulted in a set of complex algebra. We got rid of trig, and we very nicely ended up getting a much easier solution. Okay, what we found was that For an e raised to st kind of drive, my response was of the form vp e raised to j omega t. Okay, so if my input was vi e raised to st, my response was vp e raised to st. Okay, where s was j omega shorthand. So my response would be vp e raised to j omega t, where vp was a complex number. Okay, the vp was a complex amplitude of the response, and that complex amplitude was given by, for this particular circuit that we had, the RC circuit, for the sinusoidal input was vi divided by 1 plus j omega RC. And we further said that really the most important part in all of this is really the complex amplitude Vp. Okay, so this Vp is the complex amplitude. Okay, this was the really important part, okay, which is this here. And the complex amplitude contained really all the information that we cared about in coming up with our output response. So for example, once I knew Vp, I could directly figure out my output, because the amplitude of the output would be the amplitude of Vp, okay? And the phase of the output is given by the phase of Vp. So once I know Vp, I can exactly figure out what the output looks like. Further, I did not really have to, in the steady state analysis, I did not really have to follow the usual step 3 and step 4 of solving differential equations, which is figuring out the homogeneous solution and the total solution. And the reason is that these had to do with transients, and the transients simply would die away because we cared about the steady state solution. So the bottom line was that by sneaking in the vi e raised to st drive, my responses were also going to be of the form e raised to st. And the complex amplitude of the response at the output, Vp, was all that I needed to know. Okay, so Vp contains all the information we need. Both the amplitude of the output cosine and the phase of the output cosine is contained in the magnitude and the phase of Vp, respectively. Okay, so here, I just cannot tell you how exciting and interesting the exponential is. Okay, the exponential is just a fantastic signal. Okay, you put in the exponential into these linear systems, and you get exponentials all over. Okay, and the reason we end up with complex algebra is when you have various equations in these exponentials, since the form of all the outputs are also exponential, and when you differentiate them, you get more exponentials. So maybe s times e raised to st, or s squared times e raised to st, and so on. You cancel out the exponentials, and you're left with algebraic equations in s. Okay, and since s is j omega, oftentimes these are complex algebraic equations, okay, leading up to complex algebra. So hopefully that gives you some insight into why e raised to st was so important to our analysis.